Hello everyone, welcome to our lecture number 14. Today I'm going to talk about entropy and about entropy balance. How do we solve for the generated entropy in our system, or the transferred entropy, and the total change in a process. The total change in entropy when we have a process is going on in our system. So therefore, I picked this example for you, number one, which talks about, as you see in part ABC, talks about the entropy change of the refrigerant, the tank content, entropy change of the heat source, and entropy change for this process, the whole process. So we're going to cover those three topics. I need in the beginning, so as always, please keep this in front of you. So in the beginning, I need to talk a little bit about the equations and formulations. How do we solve for entropy, like our like uh, when do we need to use the table, or when we don't need. And but before I go um, through these materials, I need you to read, as I've put on the blackboard. I need you to read lecture notes number 11 and 12. They're all just talking about the concept. They're talking about second law and how do we define a process as a reversible or irreversible types. And so let me write it for you, that please read these notes in advance. So mm, lecture notes, lecture notes 11 and 12, which are talking about second law and reversibility of, or irreversibility of this process. Okay, so let's go and talk about the concept. In the beginning, I would like to define an open system for you. So that would be a combination of solid and dashed lines, right? So these two solid lines are the real boundaries that only mass can be transferred through, and the dashed lines are imaginary boundaries like opening or exit, that both mass and energy can be transferred through these boundaries. So let's imagine that this is like a cool system. So we have all types of energy, everything is going on. So I have mass going into my system, I have energy going into the system, and I have mass leaving the system and energy leaving the system. These two energies will be carried by mass. So when we write the mass and energy together, it means that these two energies were transferred through these boundaries. So we're transferred through opening, or transferred through the exit. And also, I have another energy going in through the real boundaries, which would be like heat or work, and I call that E in. But just to distinguish it from the other one, I would call that E prime in. Okay. So entropy represents some sort of chaos in your system. So when you add mass to your system, imagine that you are in a room and the door opens, and like 10 people come into your, to come in the room. So what would happen? People are like walking around, talking, making noises. They might hit something and drop that on the floor and it breaks, for example. Or they might fight, So they are making, they are bothering the system, basically. So by entering the mass, by entering these people or molecules, we are making a chaos, right? And when these people are coming into the room, they have energy, right? It's like in the morning, and they are energetic. They have energy. They can fight. They can heat, or they can talk, or they can run, or they can do any physical things, right? So they have this energy that is carried by themselves into our system. So they have the potential to make the chaos, right? So the probability that something might happen would increase. And likewise, if the door opens and some people leave the room, then this probability decreases, right? So then the chaos, the probability of having chaos would decrease. So if we define entropy as something that represents chaos or the probability of um, like intermolecular reactions, or like some sort of um, like instability, let's say, of these molecules. So then if mass comes into the system, this probability raise up, and the entropy would be more. Entropy increases. And if mass leaves, entropy decreases. So entropy can be transferred by mass. So that would be like S mass. And also, beside this mass, these two E in and E out carried by mass, if we add this energy through real boundaries like heat, then the molecules, the velocity, the intermolecular velocity of these molecules will increase, right? So the probability that they hit or they collide would increase. So again, entropy, the potential, the chaos potential increases. So entropy can increase. So either by heat, like by energy, or by mass, we can add or withdraw entropy to or from our system. So entropy can be transferred by mass or by energy. In this case, we will talk about heat. Because also work, like if you do work on the system, then the volume is changing, and then entropy will change. But that's because of like another story, because of like some constraints that you are applying to your system, that you're limiting your system, right? Let's say you shrink the system, you decrease the volume, then the entropy increases as well. But that's another story. So we will focus on heat, just heat. So entropy heat, let's say S heat. Okay. So how can I change the entropy of my system? I can add mass, or I can withdraw mass. Then the entropy would change. Or I can add heat. I can warm it up or cool it down. Then the entropy changes, right? Therefore, let's draw that with green. S can be added through these boundaries. S in. This is mass. Let's say, yeah. And then, or leave the system, S out. Right? Or the entropy, the heat entropy. The entropy which was transferred by heat. And beside all these different entropies that can be transferred by mass or energy, entropy of a system can changes um, if it is generated in the system. So all the systems that we have in the nature, they prefer when the process happens, regardless of if we have a heat transferred or mass transferred. Let's say it's closed and it's isolated, and a process is going on. There's no heat, no mass. Beside all these three green entropies that I've mentioned so far. If a process is happening in a system, entropy will be generated inherently inside these molecules. These molecules, there's like, for example, friction. Like there is a collision between these molecules. There's intermolecular collisions, and entropy will be generated by itself. By like I mean like the system, it's naturally generate generate entropy. In some cases, this generated entropy might be zero, which we call those types of process as reversible. It means if a process happens and no entropy is generated, then it's possible to reverse the process and like force it like to happen. Like it is possible that the process happens in a opposite way, in a reverse way, right? It's like play a movie, like hit forward, it goes like you see the movie, it goes like further. You pause it, and then it goes like hit on the bottom, and then you play it backward. So this might happen if the process is reversible, if entropy, the generated entropy is zero. Okay, so we have another type of entropy, another way that entropy can be can this entropy that entropy of a system can change. There's another way which is called the generated entropy, right? And it's either positive, so it will be added to the system, or it might be zero. It is not going to be negative. That is impossible. That is impossible that a process happens naturally and without any heat or mass coming into leaving the system, entropy decreases. The probability of chaos decreases. No, it doesn't happen. It won't happen. So entropy can be generated inside a system. So S, the generated entropy, if it is more than zero, larger than zero, we call this process irreversible. And if the generated entropy equals zero, that's gonna be reversible. You can play that process in the opposite way. It might happen, it can happen in the opposite way. And this generated entropy might be due to intermolecular interactions, like friction. Now you can check lecture note number 13, pages 2, 3, 4, 9. Now if I divide those two types of entropy transferred by like either mass or like heat, or together it might happen. So the formulations would be like that. So if the entropy transferred by heat, or entropy, oh sorry, yes, yes, or entropy transferred by mass. So S heat is defined sorry, on page 5 as well. Okay, so entropy can be, so the entropy that was transferred by heat equals the integral over infinitesimal portion of heat which was transferred at a constant temperature system. So let's imagine that the temperature of the system does not change, something, and a small amount of heat is added to the system. Then the and we solve the integral from like initial state, like let's say point 0.1 to point 0.2, then the whole entropy can be calculated. Or we can assume that if the process is isothermal, it means that through the process from point 0.1 to point 0.2 the temperature does not change. So then I can take out this temperature, and then the integral of delta Q would be just a Q, the amount of the heat which is transferred to the system. So like we have an exception that for isothermal processes, T system, let's say equals T0, which is constant all along the process, then S heat would be 1 over T naught of delta Q, which would be Q divided by T0. Then depending on the sign of Q, if Q is going in the system, that would be positive. If Q is heat is leaving the system, then it carries out the entropy with itself. So the S heat would be negative. We will see this sign thing in the example, right? So heat going into the system, entropy is going to increase. If the heat is leaving the system, then entropy decreases. And that when the entropy is transferred by mass, then S mass equals the amount of mass times little s, which is specific entropy, total entropy divided by mass. Like, you remember little v, little u, little h, they're all the same. So now we know that, okay, we can change the entropy in different ways. We can add mass, or we can withdraw mass, or we can add heat, or uh, heat can, like, I mean, goes into the system or leaves the system, and some amount of entropy will be generated always, unless it's reversible, and that would be 0. So I can write, oh my god, okay, so I can write, give me one more page, okay, great. Now I can write the entropy balance. So entropy, like energy or mass, has a balanced formulation, has like conservation of entropy, let's say, for example. So, and depending on what sort of system we have closed system or open system, we will have two different formulations. For, hope that you remember that for open systems, um, we have all little dots on top of all the parameters, which indicates that all these parameters are per time, right? So in closed system, like as we have, such as the example that we have here. It's just a tank, rigid tank. It's closed. All the boundaries are real in this example that I'm going to solve. That's this closed system. Um, so I have the entropy going in or leaving the system, and this will be transferred by either mass or heat or together. So I summarized all transferred entropies here in this parenthesis plus that portion, the generated entropy, that it's either 0 or larger than 0. So this inequality or equality with respect to 0 equals the change in enthalpy. They're all small, large s, and that equals m times the specific amounts per mass, which is S2 minus S1. This is final, this is initial. For the initial state of the process and then the final state of the process. And if I break this parenthesis into two parts, mass and heat, and assuming that I have an isothermal process, so once again, for isothermal process, please pay attention about this. Therefore, sigma Q K here means it's all in Kelvin, plus the summation over all the inlets and inlets, so mass times the entropy, plus the summation over outlets, MO, SO, right? Mass leaving the system, so it carried, sorry, it's a negative here. So it might leave, so if the mass leaves, it will carry out entropy with itself, plus the portion which is generated equals M times S2 minus S1. And the unit is, both sides, your unit is kilojoule per Kelvin. And if we have an open system, so it would be the same. We just have the dots. So S dot going into the system minus S dot leaving the system plus the rate, here is the rate of generation, entropy generation, equals the rate of change in entropy, total entropy of the system, the rate per time. And if the process is steady state, then that would be, the right side would be 0 because nothing changes. It would be identical. It would be the same through the, if I look at the entropy now, and if I go home and come back tomorrow, then the entropy would be the same. So there's no entropy change, total entropy change of the system in time. And in the other form, it looks like summation over the rate of heat. The total heat is just like total heat, like in and out, just a summation over in and out divided by the temperature of the system plus sigma m dot ISI plus minus, sorry, let me hold on, I'm sorry, sigma O, the m dot, the rate of mass leaving the system times SO out plus the rate of entropy generation, capital S generated, equals ds of, here I have a control volume, right, which is in my system, over dt. and the unit would be kilowatt, because everything is per time. So that would be like energy per time, which is watt. And please check 15 lecture notes, 15 pages, 10, 11, 12, 13. 10, 11, 12, 13. Okay, so we have all the material that we need. And in this example, let me bring it up once again. Here we have a rigid tank contains something, so that would be a closed system. There's no valve, no opening, no leakage, nothing. So mass, it's closed system. So we're gonna use this equation on our left here. This guy. This is what I'm gonna use. And so now, so far, we know a little bit like about entropy, like how do we treat this parameter. So let's solve our example. Example 1, this topic. Let me put a note there that you'll see later on in the lecture that in this question we need to switch between different systems. Because if you pay attention to the text, here it says entropy change of refrigerant. So I need to take the refrigerant, the tank content as my system. Then it asks for the entropy change of the heat source. Now the system would be the heat source, that it's supplying the heat, adding the heat to my system, to the to the tank content, right? So I need to change my system, switch it to something else, and then switch back. It might happen to the uh, tank content. Therefore, I'll show you, but just keep in mind that we're gonna deal with different systems. And therefore, I need to define my question step by step. So first of all, I will solve for the total change in entropy of the refrigerant. How much is that? Right? So the first step is, what is my system? Obviously, it's asking for total change in refrigerant, so I need to take the tank content as my system. So that's like tank content. Okay, and it's a closed system. So now I need to draw my system. It contains all solid lines because it's closed. There's no opening, no dashed line. And Q is going into my system. I'm adding heat. I mean, the heat source, the surrounding is supplying heat to the system. And therefore, this heat will carry entropy by itself, right? And here's my system. This is the system. No mass is closed. So all these two terms, these two summations, this one that I talked before, they would be zero. There's no mass coming in the system or leaving the system. Still, I might have like generated entropy because I'm not sure if it is reversible or irreversible. In the text, it didn't mention anything about whether this is irreversible or reversible process. And heat is going in, so I have just Q in, right? So it's easy, right? It's easy. So I'm gonna just use the equation S in minus S out, the balance, entropy balance, plus the generated entropy would be the total change of my system, right? Easy. And I'm solving for delta S system, which would be Sorry. Let me summarize. Let me simplify this a little bit because we can. So we need to take some assumptions. That the first one is no mass or heat out. No mass or heat out, right? So the S sub out would be zero. There's nothing, there's no tool or no one, basically, I mean heat or mass, to carry the entropy out of the system. So that term would be zero. And the entropy entering the system would be is only due to heat transfer because mass is not entering the system. So S in would be Q in divided by the temperature of the system. Okay, and but hold on. Is it sorry about it? Is it a constant temperature process? Let's look at the example. Mm, gives us the pressure and it's a 40% quality, so it's a mixture. Then 400 kPa. No, no, the pressure is changing, so the temperature might have changed. So it's not that. This is not right because in the in this on this page I said that the S heat is defined by this integral, right? And if the process is isothermal, then I can simplify it to this form. But it's not isothermal. It didn't mention anything about if it is isothermal, so this is not right. And S in would be like, seriously, should I take this integral? It doesn't make sense because it's complicated, right? And on the other side, what about this guy? See, I'm looking for this, right? I'm looking for the total change of the system, entropy of the system. I don't know anything about the generated entropy. I don't know anything about the temperature. So I cannot find delta S, right? So I guess it doesn't work. This guy doesn't work here because I don't know how temperature of the system changes. I don't know anything about the generated entropy. So this does not work. Then what should I do? How can I find delta S? Well, let's go a little bit in detail. I know that based on the text, I have initial and final state. In the beginning, I know pressure and I know the quality, and then I'm adding heat until the pressure rises to that much. So if I define this like as the initial and final states, and then use the table like point 1, point 2, and our famous summary table, then I can solve for entropy in the beginning and entropy at the end, and then subtract, and that's it, right? So we need to use property table like A11, 12, and 13 for R1 through 4A. Oh, I'm happy. So then delta S would be M S2 minus S1, but I'm sorry, I do not have any idea about M, S2, and S1. But I'm sure that I can solve for those. I can use a table and I can do it. And now our famous table comes into play. Point one, point two. Okay, great. it says that the tank is rigid, so volume would remain constant. So V1 equals V2. Okay. In the beginning, it says that pressure is 200 kPa, and we add heat until the pressure goes up to 400 kPa. And in the beginning, we have the quality of our mixture, liquid vapor mixture, which is zero point 0.4. That's all we know. And I need to solve for mass, S2, little s2, and little s1, one by one. So let's go at point 1. Okay, I guess now you are all experts, material, in to find, how to use the tables and our summary table as well. Anyway, so please, this is the material, and we have a quality, which means it's a liquid vapor mixture, right? And that's good, that's good. I'm looking for mass, okay? I'm looking for mass. And I know that mass equals the total volume divided by a specific volume, right? And mass is constant because it's closed. So I can just pick these two values at the initial state. But now I need to solve for little v. Then I will put it there and divide v1. I have it's zero point 0.5 meters cubed, and then I can solve mass. It's easy, right? So I have the pressure, I have the quality, so I can solve for little v1, and I know that v1 equals vf plus x1 vfg. Um, yes. So at 200 kPa. So if I go to the table here at 200, the A12 at 200 kPa, where is it here? This is VF there, and this is VFG. And the difference in between those would be VFG. Sorry, the second one was VG. So that would be, and it's zero point 0.4. The quality is 40%, and I need to subtract VG from VF to find VFG. So the whole parenthesis is VFG. And then V1 would be, so now we are helpful. We are sorry, hopeful that helpful. We're hopeful that we can do something right now. Now we can solve for M, and likewise we will be able to solve for S2 and S1. So this is the total volume divided by specific volume that I just found at point 1 at that specific pressure. So this is the mass, right? Great. Now let's go back to the equation that we want to solve. We want to solve for the total change in entropy. So next step is to find these two S1 and S2, little s1, little s2. So I'm going to do the same process at point 1 and point 2 and solve for entropies. I'll stay at point 1, so I'll continue that. Once again, entropy can be solved like little v, like specific entropy, like specific volume or specific enthalpy. They all can be solved by this famous equation. Then once again, if you go, the pressure is 200, okay? So at this pressure, if I continue all the way here, this guy and this guy, these are SF and SFG. Please be careful that the for a specific volume, the first and second columns are Vf and Vg. But for internal energy, enthalpy, and entropy, the first and second one are Uf and Fg, and the third one is Vg sub g. So these are a little bit different than these two guys. So I'll just put those numbers in my um, sorry, equation. Then here is the quality, and then 78339 equals 4678. Awesome. And the unit is kilojoule per kilogram Kelvin. You can check it out on the table. Now I need to switch to the other point, which is the final state. And once again, the material is R134A. So I need to I forgot to mention here that I checked all these values at A12. Now let's go to now at point 2, based on our summary table, pressure is 400, right? So if I go to my table again here, 400 is there. But wait a second. At point 2, we just know the pressure. See? Let me show you on the table, on our summary table. That's all I know. I just know the pressure. At this pressure, it might be subcooled, it might be liquid vapor mixture, or superheated. I'm not sure. So somehow I need to find like a link in between point 1 and point 2. And if I pay attention, I have the link right there. Do-do, do-do. It's a rigid tank. Volume remains constant. Mass is conserved as well because it's a closed system. So the specific volumes would be the same. So at this point, I don't know what the status is. I don't know what the mixture is. So I need to solve for this guy. If I got x2, then I can do the same procedure that I did here. Go to the table at 400 kPa, find SF and SFG, and solve for x2 separately, then put it back there and find for S2, right? So M and V, mass and volume, are constant. Therefore, V over M equals V1 equals V2 equals, we just found it before, up there. Okay? So, at now I have the specific volume, right? Now I need to judge. I need to test or check that with this specific volume, where am I on this table? Am I somewhere in between these two values? Or did I pass the specific volume of saturated vapor? Or am I lower than a specific volume for saturated liquid? Then based on this, based on the comparison between little v2 and Vf and Vg at that pressure, then I can decide that what is the status of the mixture, or I mean like of the system. So Vf at 400 kPa is, according to the table that I showed you right now, and Vg at that pressure was this much. Okay, now I need to check that this number, is it between these two guys? Yes, it is. So V2 is in between Vf and Vg at this pressure, which means it's still a mixture, right? You're in between saturated vapor and saturated liquid. So it's a mixture. It's a liquid vapor mixture. Now our responsibility is to find x2, because if we are having mixture, we should know what is the quality. And all based on table A12. And x2 is defined as V2 minus Vf divided by Vfg equals once again Vfg equals Vg minus Vf. So x2 would be dun, 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 dun. That's it, and it's unit dimensionless. If you don't remember how I did this, if you don't remember that equation, check this page 13 on lecture note number 6. Now I have S, so again I can go back to the table. I know it's a mixture. Here's SF, here's SFG, and I know the quality. Then I can simply write S2 equals SF plus X2 SFG, which would be everything at 400 kPa. 24757 plus the quality times this guy, which is done 54 SFG equals 7813 kilojoule per kilogram Kelvin. Okay, please don't get lost. We want to solve for delta S. It's mass times S2 minus S1. And all little s. Everything is per mass, see? Per mass. And we were successful. We found them all. 37 kilograms times S2. I just got it. Minus S1 that I solved before. Up there. Kilojoule per kilogram Kelvin. Goodbye, goodbye. Then delta S of the refrigerator, this is what I picked as my system, would be 3.876 kilojoule per Kelvin. Ba-bam. Okay, so we found the entropy change of the refrigerant. Now I need to okay, now we can go to the next step, next question, which asks for heat source. Sorry, the entropy change of the heat source. So the question is telling us that we need to change our system. So here the question is total change of entropy of the heat source. Right. Okay, and it's like saying that you need to pick the heat source as your system. This is why in the beginning I told you that we need to change, or like it's a reservoir. This is why I told you that we need to change our system in this solution. Page 4 talks about reservoirs. Oh, sorry. So my system would be like the rest of this, the rest of the, like, here's the environment, for example, surrounding, I mean. So here is my system, not the tank. Whatever is other than the tank. And the system is losing the heat. So Q, so it's Q out. And therefore entropy is going to leave the system. And it's going to go into our previous system, which was the tank content. This is just a trick. The switching between systems, between heat source and tank as a system, this is a trick. I'll tell you, you'll see in 1 minute. Why am I doing this? So again, I will start with this famous equation, plus S generated entropy equals the total change of our system, which is the heat source, right? The heat source is the surrounding reservoir around the tank. For heat source, which is some sort of a reservoir, for the entropy is the entropy would not be generated, and there's no entropy going into the system because we are just losing the heat. We are just transferring the heat to the tank. So S out is just the S due to heat transfer, right? So this is 0, this is 0. Therefore, delta S source equals minus S out equals minus Q out divided by T source. Here I write the subscription as source because the system is the source, heat source. The system is the reservoir, the surrounding. So to find the total change in entropy of the source, I need to solve for, this is given. In the text it says that is 35 degrees C from a source at that temperature. So the system now, which is the heat source, is at this temperature. And the temperature is constant in reservoir. See, this is the trick. I'm switching to another system just to be able, just to get the permission that I can assume temperature is constant. This is the trick. We change our system, we define the surrounding as the system, then we claim that, okay, now the heat source or reservoir or surrounding is the system, and we know that the temperature of the reservoir doesn't change. Yes. So here we can assume that temperature is constant, so we can get rid of the integral. And all I need is heat. How much of heat is transferred between the heat source and the tank? Right? This is all I need right now. So I can just pause again and go back to the previous section. Go back to tank content as the system. Now again, here is my tank, here is my system, and I have Q going into my system. And I can use my summary table. X2, sorry, I forgot to update it. That X2 is 0.7813 kilojoule per. Uh, no, sorry, it's dimensionless. Yes. So now I have pressure and the quality. I can solve for energy, internal energy, and likewise at point 1. And by use of first law, I can solve the heat. How much of heat went into my system there, and that is exactly the same amount that is leaving the surrounding, right? It's just heat is transferred from the surrounding to the system. They're same values, right? The absolute values are the same. Therefore, S is going in. Anyway, I'm not gonna. I don't care now about this entropy. So take a look at these pages, please. 11, 12, and 13. And according to first law, we knew we've talked about this in previous lectures. Oops. That Q plus W, it's a closed system, plus sigma m theta, all through inlet, minus heat, work, and mass transfer, all through outlet, equals m, total change in energy, right? This it's closed, gone, gone. No work, boundaries are fixed, doesn't move. And here Q is going into the tank content, so please be careful. I just switched back to the content, tank content as a system. So Q out is 0. And potential and kinetic energies are 0. So E would be internal energy, would be U, because we don't have velocity or gravity, something mentioned here, nothing. So Q in would be mass times U2 minus U1. I've got the mass in previous pages. So all I need to do is just go back to the table at like point 1, for instance, and or point 2, and say at this pressure, internal energies are these two numbers, right? And use that famous equation and solve for U1 and likewise for U2. So at point 1, P1 was 200 kPa. So U1 is UF plus X1 UFG, and that would be 38.26 plus. I got all these numbers from the property table, table A12. 0.25. These are the internal energies UF and UFG at this pressure, and that was 112.2 kilojoule per kilogram. It's per kilogram. It's specific. It's little u, and likewise at point 2, P2 was 400. So again, you go back to that table. This A12. Now U2 would be UF plus the second mixture, and that was and please see, now you realize the importance of the summary table, that you can just look at the table and find x2 or x1 or anything that you're looking for. So, oh, no, sorry. 198 point. Okay, now we were looking for Q. We were looking for how much of heat is transferred between the heat source and the tank to the tank. Put it back there, and this is the temperature. Then solve for delta S source. How much was M? 12.37 kilogram times U2. U2, where are you? Who you want? Hello? Okay, that was 1058 kilojoule. So this is the heat. This much of heat is transferred between surrounding to the system. Therefore, and it's the same amount. So Q out for source would be same value. Well, the direction is different because Q is going out of the source into the tank. So it's just out. Just keep in mind it's like about it's leaving the source and it's entering the tank. So now delta S source, let's check this out again. So I defined the surrounding as my system, and I said that the generated entropy and the S in are all zero, and the S leaving the system, S out, is just the heat. It's just the entropy carried by heat. And now, since the my system, which is the surrounding, is at the constant temperature, I got rid of the integral and I simply wrote it this way. And now I have this temperature. All I need to know was actually the value for Q that I got. So I just put everything back there. Minus 1. This was the energy. And this is the temperature, which must be at Kelvin, not degrees Celsius. So that would be 3 point kilojoule per Kelvin. Kilojoule per Kelvin. That is what we were looking for. And the second question asks for the total change, that if you look at these pages on number 13, lecture note number 13 for these pages, you'll see that the total change of entropy of a process, it's the summation of delta S of the refrigerant, sorry, plus the delta S of the source. Totally, we have the tank and the surrounding. There's nothing else more. There's nothing else, right? Either the tank or whatever other than tank, which is the surrounding. And we got that here, that the change in entropy of the tank, the refrigerator, was that, and then the total change of entropy of the surrounding was this. So I need just to add them all. And please keep in mind that the summation of these entropies should not be zero, because entropy is generated. See, this is the generated entropy. In total, right? Something happened, heat transferred between the heat source and the tank, and the total entropy just came up. This is the total entropy that is now there, right? So if you didn't want, or like the person who transferred this heat from the heat source to the tank, if that person was not looking for increasing the entropy, we should say that he made or she made a mistake. That by doing any process, if you cannot keep it as reversible state, reversible process, some amount of entropy will be generated. Unless you keep it as a reversible process, then it would be zero. No entropy will be generated. Thank you for listening to this lecture, and sorry that it was long.